Okay, let's get started. Okay, so this probably, I'm guessing this might be the last chapter we'll be doing. So we're going to learn about bearings and bearings just because they're probably the most important part in a machine element other than the shaft. The shaft holds on various components, gears, motors, so on. Bearings basically transmit the forces from the shafts to the structure and eventually to the ground. And you want to have a good bearing, obviously. So there are two types of bearing. There is the roller bearing and then the ball bearing. This one is the ball bearing because you see there are balls. So a bearing has usually three parts: the inner ring, which is this one, the outer ring, which is the outer part, and then between the inner and outer ring are these balls. And they just shown two, but then they are all over the circumference. And sometimes those balls would have separators just to keep the balls from contacting each other. And that is something you'll find in a more expensive bearing. Cheaper bearings will not have those separators. So what does the bearing do? The main goal of a bearing is to constrain motion in only directions you choose to constrain. So for example, when an object is in freedom in space, it can move in the XYZ direction and also rotate over the XYZ axis. So it's 6 degrees of freedom. But the moment you put a bearing on that object, it basically constrains motion to only 1 degree of freedom, that is rotation about the axis. In this case, that's the axis of rotation, and so it will rotate. So when you have rotation along one axis, you're not wasting energy, right? You're only allowed to move in one direction. Okay, so that's introduction. These are host of bearings. I won't go into deep for any of them. They just depend on the application. You'll use a different one. And when you read see the bearing and look at the application, sometimes it's kind of obvious to see why you need a particular type of bearing. Yeah, for example, self-aligning bearings would help you to take care of misalignment. Just an example. So in general, more the number of balls, you have the greater load carrying capacity. And in general, bearings will be subjected to two types of loads: radial load, which I've shown here, it's along the radius of the bearing. And then there'll be an axial load, which will be along the axis of the bearing. And not all bearings will be able to take both those loads. And in fact, you need to look at the catalog and see which of those loads, which bearing takes which of the load, how much load it can take, and use those values to figure out what bearing you would need for your own purposes. These are some examples of roller bearings. So in this case, they are not balls, but rollers. And the reason why you want rollers is because balls have limited, so the way bearings carry weight is through the contact area of the balls, and balls make contact at one small part over their surface, while roller bearings make contact over a bigger surface area, which means that they can take more loads than what ball bearings can take. And so heavier industrial applications would use roller bearings over ball bearings. Again, they're clearly more expensive than ball bearings. Okay, so what goes into what really goes into choosing bearings for application? That's what we'll do in this part of the course. Okay, so let's get started. 11.3. We'll learn about bearing life, bearing load life at rated reliability. So just like shafts, we're interested in the life. And we, in this case, are also interested in a term called reliability. Reliability is the opposite of failure rate. So if something has a high failure rate, it has low reliability, and low failure rate is high reliability. Okay, in general, this is what a layman definition of bearing life would be. So bearing life is the total number of revolutions since things are moving in circles. Okay, so revolutions is one way, or you could also write it as hours. So some people, revolutions has not much meaning compared to say hours, like it'll work for 3,000 hours or 5,000 hours. But when you talk about hours, you want to say at a constant speed. So you specify the speed of pairing operation until failure is developed. So bearing life is based on figuring out the revolutions, okay, or hours. Okay, now let's get a little bit more specific. So something called a rated life, and this is the spec which you'll see in spec sheets. Okay, so this is the definition. This is the number of revolutions. Okay, again, or hours at a constant speed, okay, that 90% of a group of pairings will achieve or exceed before failure develops. Okay, so this 90% reliability is what it's called, is also known as, this is also known as minimum life. Okay, it's also called as L10 life or B10 life. Okay, so the most common rating life is what we've seen before, shafts 10⁶ revolutions. Okay, so here's the thing. When you want to think of the life, you want to, this is, the definition says that you only look at all the bearings and you want to keep, let's say, loading it or keep cycling it, keep making it in use, and keep observing the bearings till you see that 10% of the bearings have failed. And once 10% of the bearings have failed, you stop, you see the number of hours or revolutions and say that is the rating life of the bearing. That's what it says. Now, 90% reliability is a very low value, right? In my experience, I mean, I think that we want to probably go for a very high reliability. So this is a more of a historic thing than a more, it's based on, it's been adopted for a long time, and so people didn't want to change it to 95% or 99%. Or these days, you can get much higher reliability bearings. So we'll stick with that as they have, and I'll show you a method to compute the reliability, compute the rated life for a bigger or different reliability, say 99%, which will come a little bit later. So it's based on a distribution, which we'll see later. So let's work with this definition now. All the catalogs are developed based on this definition. Let's see. Okay, so here is a plot which comes from empirical data. So what you do is you take a bearing, apply a force F, and then keep spinning it, and then see when 10% the bearings fail, and you make one of these dots. Okay, then when you perhaps increase the force, and then you'll get another point, and so on. So when you do this experiment and do a log plot of F, which is the force load to life, you see that it nicely sits on a straight line. Okay, so this is at 90% reliability. So this is nice. This is just like the SN curve. Once you have this line, you can model this line. The model for this line is, so the same, if you remember, the same arguments are true. You need to write the equation of this line as y equals mx plus c, where y will be log f, x will be log l, and then do the logarithmic transformations and then get rid of the logs. So if you once you get rid of the logs, you'll see that the expression for f and l is something like this: f times l raised to 1 over a is a constant. Okay, so if you draw a plot of f versus l, not log, but f versus l, you see a curve, and you will not really be able to get this simple expression because that curve doesn't really mean anything because it's a curve. But the moment you do log, you see it's a nice straight line, and that's why people normally draw log plots for this. Okay, so this is a constant, which is a really nice equation which can be used for design. In this case, a is a constant. A is a constant. It just depends on the bearing. A equals 3 for a ball bearing. And A equals 10/3. It's a little bigger than 3, 3.33 for a roller bearing. Okay, these are again empirical curves obtained from very arduous experiments, scaling a bunch of bearings by loading them on a force and running an experiment several thousand times. There's a little bit more definitions, and then we are all set to see how to use this to select the bearing. Okay, so let's, I want to define, what's this? Left out somewhere else. Okay, so let's define what is known as a catalog load rating. This is the one which you'll see in catalogs for bearings. So it's called the catalog load rating. It's also denoted as C10. Okay, so the definition is, it is the radial load, okay, not the actual, but the radial load that causes %90 of bearings. By bearings, it really means the ball bearings to survive at the bearing manufacturer's waiting life. Okay, so what this means? Well, let's say FR, LR are catalog, load, rating, and life. Okay, so that's something which, if you open a catalog for roller bearing or ball bearing, you will see that they'll be given an FR, LR. FR is also sometimes called as C10, as I said here. Okay, and then let's say that you want to have an application where you want a different, you have a different desired load rating, and consequently, if you have a different load rating, that is, you have a different load which will be applied for that application, then you get a different life. And your question, and the problem is to figure out what that life is if we choose a bearing from the catalog. So we just use the formula which we've seen. F times L is a constant. S times L raised to 1 over A, sorry, is a constant. From that formula, we can write FR LR 1 divided by A, FD LD 1 divided by A, and they're equal. So typically what happens is you would know the force in your application. There's a desired force. You will go choose a bearing, you'll get FR LR, and this will give you a value for LD. And then you'll ask yourself, in my application, is this life good enough? If not, then you choose a different bearing, compute the FR LR again, find the LD, and you keep doing that till you find a corresponding life which meets your expectation. Yeah, and so we'll see a problem where we do that. Now, sometimes people like to not use LD. LD and LR are in revolutions, and you want to use something else. So L, by the way, L in revs. Okay, so sometimes it is more convenient to express life in hours. For this, we'll use this symbol in math. It's a, I guess we'll say, I call it capital L here, different from the small l. Oh, sorry, the L I've been using. I don't think it's a Greek letter. At I'll call it abbreviated L. At a given speed in revs per minute. Okay, so this is just trying to put to find an expression in L, which is in revs per minute, and the abbreviated L. So this L is now in hours, and we want to now convert revs to hours. So what you do is we know the speed, which is N, so rev per minute, and then 1 minute of, sorry, 60 minutes is 1 hour. So this conversion will work like this. So in other words, L equals 60, the abbreviated L, times N is our formula. Okay, so this is just saying if you want, you don't want to work with revs L, then you want to instead work with abbreviated L, which is hours, then use this formula. But you need to specify the speed N. Okay, so one more thing, and I'll let you go and we'll do the problem next time. Okay, so we can rewrite this formula in terms of the abbreviated L, that's all. Let's do that. So F R LR 1 divided by A is FT LD 1 divided by A. Now let's sub in the value. So 60 speed, abbreviated LR 1 divided by A equals FD 60 ND, the abbreviated LD 1 raised to A. So FR is FD. You can either write it as LDLR. So this is not the abbreviated one. Equals FD XD, and I'll define XD in a bit. Or you could also write this as FD, the abbreviated LD ND divided by abbreviated NR. Okay, so these are the formulas which you should know. Okay, so what's XD? XD is, as you see, it's LD divided by LR. It's basically a dimensionless multiple of rating life. Dimension. So, multiple of rating life. And it's a dimensionless number. Okay, so if you are given FR and FD, then this basically gives you a way to compute the life. Okay, a bearing company rates its ball bearings for a bearing company rates its ball bearings for 1 million revolutions for 90% reliability, a desired life of 5,000 hours at 1725 revs per minute, and a load of 400 lbf. Compute the catalog rating. So when we talk about catalog rating, we are talking about the C10 rating. So that is the unknown. Okay, it's what else do we know? We know that the bearing company rates its bearings for 1 million revolution. So L R, R is the rated, R here abbreviates rating. 1 million, so 10 raised to 6 revs, 90% reliable and desired life. So this is the desired life, but now note that it is in hours and not revs. So I need to use that abbreviated L, call it LD equals 5,000. The speed is ND is 1725 rev per minute. And then the load is given, which means that FD is 400 lbf. Okay, so C10 is asked. So what we do is going back, we see that the formula is this. So here the formula is given in terms of abbreviated LD and abbreviated LR. But what we can do is let's start from here, this formula, first one, and then use that formula and then sub in the value for LR in terms of abbreviated LR. So let's do that. F T LD 1 over A equals F FR LR 1 over A. Now in this case, C10 is nothing but the FR, the rated load. So let's write in terms of FR. FR is FT T divided by LR 1 raised to a. And since we're given, we're not quite given LD, but we're given the abbreviated LD. So let's just sub that in. LT times ND times 6T to convert the minutes to hours. 1 over A divided by LR. Okay, so C10 is FR equals FD, which is 400, LD, which is 5,000, ND, which is 1725, T divided by LR, which is 10 raised to 6. And the constant for ball bearings, so the constant for A is essentially 3. Okay, so subbing in the values, we have C10 equals FR equals 3 to 11.4 pound force, and that's the answer. Okay. Okay, so that was a straightforward problem. Let's now move on to a different topic where we'll talk about reliability versus life. And for that, we need to use what is known as the Weibull distribution. So let me just start with that. So we are in section 11.4. Reliability versus life. Full distribution. Okay, so what is Weibull distribution? Well, when you model some phenomenon and that phenomenon is probabilistic, what you do is you essentially run the experiment and you collect data, and then you see what sort of distribution follows. So for example, many things in the world, like for example, shaft diameters or most production of machine elements follows a normal distribution, which means that, let's say that if you randomly pick a diameter in a sample of 1,000 and the nominal diameter is supposed to be 1.5, then you will see that most of the diameters are in the range 1.5. In fact, you will see that 95% of the diameters are in between what they call plus or minus 3 sigma where sigma is the deviation. And so you have this thing called normal distribution, which explains most of these things. In the case of failure of ball bearings, when people did these experiments, they found that failures follow what is known as a Weibull distribution. And what this figure shows is pretty much that. That is, when you study the failure and you make a plot based on experimental data, you'll see that there is a peak like this. This is basically where most of the bearing, a big percentage, in this case, 1/4 or 25% of the bearings will have something which corresponds to about 1/3 of the life of the bearing. So you can see on the x-axis there's 1 through 12, and this is in some units, but 1/3 of that basically peaks at some point, which is not exactly in the mean, which at the middle or at 6. Okay, so that's the Weibull distribution for you. And you can fit a curve, and the dashed line is a curve which explains, which is basically the Weibull distribution. So this plot here is known as a PDF, or a probability density function, f of x. So maybe just make a note here. It's empirically found that probability of failure of ball bearings or bearings in general follows a Weibull distribution. F of x here, as I said, is the probability density function. Okay, so the rule is that if you integrate the area under the probability density function from minus infinity to plus infinity, you should get equals to 1, which means that the probability can only take a maximum value of 1 and not bigger than that. So in this case, since we are interested in the L10 life, we are pretty much looking at 10%. So you can see on the y-axis is the failure. So 10% failure is our cutoff. So you just extend this, see where it intersects the Weibull distribution, drop a vertical, and then the area here all the way beneath the curve and to the right of the red line is 90% of the complete area. It's the 90% reliability for you. So L10, this is the L10 coordinate, because L is life. So L10 is the coordinate on the x-axis such that 90% area is yellow, the one which I've just shaded. Okay, so why do we need this? Well, I'll come to that in just a bit, but let me just write a formula which relates the reliability, in this case, the area under the curve, with the life, or in this case, I'll parameterize the x-axis with the variable x. And once we have that, I will show you why we actually need it in this case of predicting bearing life. So the formula which gives me the reliability as a function of x, where x is the life, is given by this x minus x0 theta minus x0 raised to b. You note that it's an exponential, e raised to this whole thing in the bracket, in the square bracket, it has to be raised to e. So x is the non-dimensional life. In other words, it is L divided by L10. So you normalize against the L10 life. X0 is the minimum value of x. So this will be given to you. The moment you have a Weibull distribution, you will be given x0. Theta is the characteristic parameter. It's also a constant, just like x0. It is 63.21 percentile for roller bearing. And B is the shape parameter, which is 1.5 for roller bearing. Okay, so basically you are given the values for these constants. Basically, the value for these parameters depends on the shape of the Weibull distribution. And there are many types of Weibull distributions. And you can read about it in Wikipedia. Okay, so why are we doing Weibull distribution? What Weibull distribution helps us do is we have so far computed the bearing life at 90% reliability, but what if we want to find the bearing life at 95% reliability or 99% reliability? This is where the Weibull distribution will help us. So the next section actually will show you how to go from 90% to different 95 or 99% reliability, which is more relevant in some applications, right? 90% reliability is a relatively low reliability these days. So relating load, life, and the life load, life, and reliability. Okay, so what we've done so far. So far we have at 90% reliability, we have FD LD 1/a equals FR LR 1/a, where FR we also wrote that as F10 L10 1/a. So R is the rated where rated is also the R10, L10, or the F10. So it's really it's synonymous. So this is something which is available in catalog. Given in the catalog as a spec. So this is the number which you use in order to choose the bearing. Okay, now, as I said, the problem we are dealing with is 90% reliability is not that great. What if you want to find the rated load or the life at 99% reliability, 95% reliability? So how do we compute FD LD at 95% or 99% reliability? Yes, that's the question we'll be dealing with in this section. Here, what we essentially do is we use these equations, which I wrote down, and something about the Weibull distribution to make that, to compute those things. Okay, so before that, let me draw that curve. This is a curve I had shown. See, where is that? Yeah, here, right here. So a curve of log F versus log L is a straight line, as you can see, and that is at 90% reliability. So let me just draw that curve first. And then good enough. So log F log n, and then this is our 90% reliability line. Okay, so what happens is if you want to do the same experiment to find the reliability at 95% or 99%, it so happens that you will end up with lines which are parallel to this line, something like this. So this is for a constant reliability, but the reliability is increasing from 90%. Okay, this is line of constant reliability. And then if you do the same experiments at lower reliability, then you end up with lines like this are decreasing from 90%. Okay, so what do you expect is if you do this at different reliabilities, then you'll get lines which are essentially parallel. And so you could potentially do that and get this curve, but that will take a lot of experiments. So what we do is instead of using more experimental data, what I'm going to show you is how to use that Webwell distribution to go from one of these lines, say this one, which is the load line at a catalog rating, to this line or this line. So it will give you basically the load line for a different reliability. That's what we're after. Okay, so we will use Weibull distribution. And load line to compute C10 at a different reliability. Okay, so let's see how to do that. Okay, so I'm just going to draw strange. Okay, works now. Okay, I need to draw two more lines and you'll get started. That's strange. Huh. No, why it's not. Okay, that's better. Copy. Okay, so let's see what we have here is the log x, which is log L divided by L10 plot, so it's non-dimensionalized. And then we have log f, the load. And let's say that the line I've drawn here on the right side is the 90% reliability line. And this is an unknown reliability, or either unknown or you're maybe given the reliability, but it's going to be offset from that catalog line. This is the catalog by a fixed distance. Okay, so here's what's going on. Let's say that we are interested in a design where we want to compute either the FD desired. So we're given FD and we are told to compute XD at a reliability RD not equal to 90%. We write that down. Problem is compute FD or XD at R equals RD not equal to 90%. Okay, so it could be 95, 99, whatever. However, we do have the catalog rating because we have the manuals for the bearings, and that line is the other black line at 90%. So we know. So let's say that one point on this line is, draw that in blue, is this point, and that is something which we know the value of because this is a catalog line. So let's call that X10 because we know the value from the catalog, and then this is going to be the either it's a C10 or, so let's just call that C10. Now, when you draw this line, when you see the dashed line I drew, that line intersects the horizontal line at A, intersects the line at R equals RD at some point. So let's call that point the point B. And we can see that the C10 is same as FB because it's a horizontal line and the force or the load is going to be the same. Okay, so what we are doing now is we know we know C10, we know X10. We now use the Weibull distribution in order to find what this point is, B is. Okay, so that was the equation I wrote down. And then once we know we are on B, the line which passes through B and D follows the same equation, that is F times L is a constant. So let me write that down here. So the equation is F times L raised to 1 over A is constant is true for this line. It's the same true for this line, but since we are interested in relating B to D, I'm just writing it down for that one. So I'm just going to write down what I said. The solution is step 1, use Weibull to relate A and B along same load FP, which is equal to C10. And once you do that, use F times L raised to 1 over A equals constant to relate P and T. Okay, and that's, once we do the steps, we can actually compute the life or the load at R equals RD. So let's do that. Okay, so first for line BD, I actually do step 2 first, step 1 later. So step 2 for line BD. Okay, so if you recollect, BD is this line at reliability R equals RD. We know that FL raised to 1 over A is a constant. So we can write FB equals FD XT divided by X 1 over A. Call that equation 1. That was easy. And now what we'll do is at B and A, we have we can relate A and B using the reliability equation, which I wrote down earlier. So for B and A, long constant FB, we have RB equals exponential XP minus XO divided by theta minus X O raised to minus. Let me check if I got this right here. Yeah, so same equation here. Okay, so let's now solve. So this is a reliability equation, but let's solve for XB and note that RB equals RD. That is, in other words, the reliability at B is the same as the reliability at D because this is the constant reliability line. So we just put RB equals RD and get XB equals X0 plus theta minus X0 1 divided by RD over B. This is our equation 2. We circle the 2 important equations. This is one of them. And this is the second one. Now, if you want, you can also combine both this equation. Combining 1 and 2. So this is just doing it in one step. We can write the C10 life at a different reliability, R equals RD. Okay, what is that? It's basically the reliability at, in this case, F. So it's at FB. FB equals FD times XT X0 plus theta minus X0 natural log 1 divided by R T 1 over B times 1 is 1 divided 1 over A. Okay, so you can use this equation to find the C10 life at a reliability which is different from 90 degrees. Okay, so let's see how to apply this in a formula, in a problem. Okay, the design load on a ball bearing is 413 lbf. The speed of the shaft is specified as 300 reps per minute. The expected life is 30 kilo hours at a reliability of 0.99. Compute the C10 catalog entry on the basis of 10 raised to 6 revolutions of rating life. The Weibull parameters are given, x0, theta minus x0, and b. Okay, so let's try to sort of parse these values in terms of the variables we've identified before. So the design load on a ball bearing, that is the load which is desired, which we want to design it for. So Ft equals 413 lbf. The speed of the shaft is 300 revolutions per minute. So now, since this is revs per minute, this should be n was 300 revs per minute, and this is desired. So let me just put nd here. The expected life is 300 kilo hours. Okay, so since this is the life is in hours and not revs, this should be the abbreviated L, and this will be LD because that's desired. So 30 kilo is 10 raised to 3 hours. Okay, the reliability at D is 99%, or just put it as 0.99 in the formula. You have to put a number less than 1. Compute the C10 catalog entry. So we need C10 at R equals 0.99 on the base of 10 raised to 6 revolutions of rating life. Okay, and Weibull parameters are given. So x0 is 0.02, theta minus x0 is 4.439, d is 1.483. Okay, and then there's one piece which I forgot to add. 10 raised to 6 is the rating life. So it will be that will be LR. R stands for rating life, 10 raised to 6 reps. Okay, so first let's just work it out backwards. Let's write down the formula for C10. So C10 at a different reliability is the formula from which I copied from, which I'm going to copy from right here. This is essentially what I'm going to write. So FD XD x0 plus theta minus x0 natural log 1 divided by r t 1 over a, sorry, 1 over b. Then this whole thing is 1 over a. Now this is a ball bearing, so I'll just assume a is 3. Okay, so let's see what's given, what's not. C10 is unknown. XD, x0 is given. Theta minus x0 is given. The reliability at D, this is given 0.99. And so FT is the desired, so it's also given. However, we are not given XD. This is an unknown. So once we find XD, we can sub in the value for XD and compute C10. So how do we compute XT? Well, we're given the, so we are given, so what's the definition for XT first? XD is LD divided by LR. Okay, it's the normalized value for the life. So we always divide the desired with the rated life. So LD is given, LD is not given, but the abbreviated LD is given. So let's write that, relate them. It's 60 abbreviated LD ND divided by LR. So 60 times LD is 30 times 10 raised to 3 divided by LR 10 raised to 6 and that comes out to be 540. So now let's sub that in the first equation.
Professor, do we have to put the and day value as well, like 300?
Oh, did I miss that? I'm sorry. LD, yeah, I missed it, sorry. $300. Okay, the answer is right. I just copied from the notes. I just forgot to add the 300, 540. So let's sub that in. So we get C10 equals 413 540 divided by 0.02 plus 4.439 natural log 1 divided by 0.99 raised to 1 divided by that would be B. B is 1.483 1 over A. So if you do this calculations, sorry, A is 3, you get C10 equals 5580 lbf. Some space for this. Okay, can't move this, quite move it. C10 is 5580 lbf. Okay, so that's